Dimensional control systems is focused on dimensional engineering. We help customers leverage their CAD, PLM, and quality management systems to make efficiency gains across engineering. We're focused on the front end, where we help customers do assembly variation simulation of the digital design model. We are also experts at the back end, when you start collecting quality or measurement data from your manufacturing plants and manufacturing partners. We are focused on our place in Industry 4.0. The objective of Industry 4.0 is to combine existing technologies, CAD, PLM, QMS, with emerging technologies, 3DCS, for example, to make operational efficiency gains across engineering. The fundamental underpinning or digital seed of Industry 4.0 is the geometric dimensioning and tolerancing. For most companies, that currently resides on the drawing. But all major CAD systems now allow you to embed this 3D GD&T as a semantic feature in the CAD model. The more important element here is that now the GD&T is a machine readable and reusable file. So other elements in every manufacturing business will take advantage of it. Inspection, machining, robotics. This leads to operational efficiency gains right out of the gate. Here's the old school, right? We design it, we've got to engineer it. We spend a lot of time, money, effort with really smart people to get to a physical build. We spend a lot of time, money, and effort with really smart people to get to a physical build. And we go back and forth before we get to launch so that we can validate and verify our design is going to meet quality requirements. Every manufacturing business has three fundamental efforts. Product engineering seeks to plan for quality. Manufacturing seeks to be lean. Manufacturing seeks high yield or the most efficiency possible out of the plant. And quality management keeps track that we are complying with a quality spec. The red wheel is the program. And those fundamental efforts take place, but today, a little bit autonomously, a little bit separately, and the line of communication between those efforts is often slow and delayed. The program is going to go, but there can often be delay when it comes to the data that comes out of these efforts. But now, with the Dimensional Engineer's Toolbox from your CAD desktop, you can make datum strategies digitally. You can benchmark your design before you cut any parts. You can optimize fixture locators without math data of the fixture. You can simulate multiple build scenarios. This puts you in a position to go to your launch with plan B, C, and D for the build, along with a mitigation plan should issues crop up in the launch. We want to collect data to make decisions. Get data from suppliers. Make them validate parts before they ship. And start to thread the language of manufacturing, GD&T, through your teams. This will be the fastest way for communication across these efforts. Now, with dimensional engineering in the middle of the effort, now those APQP, lean manufacturing, and quality teams are all in sync. And more importantly, they're all in sync with the program. When the program needs data, they can go to the system and get it today, not tomorrow after a decision needed to be made. The new school will have you apply artificial intelligence in its purest form at the front end. Make decisions, create machine readable GD&T that can be shared. And so now we go to the build faster than ever before. We're making engineering decisions 2 to 3 times faster. We are making engineering decisions 2 to 3 times faster than ever before. We still have to get to a build, that's obvious, but do so much faster and a lot less expensively. Sikorsky has been building helicopters for over 90 years. For all that time, they would get to a point in the build schedule after all the engineering effort, all of the tooling, all of the design effort, supplier quality assurance. They would get to the point in the build schedule when they wanted to locate the transmission to the structure. They knew it would be 2 weeks to make the adjustments required to both install and make functional that very complex interface. With 3DCS, Sikorsky told ASME, the American Society of Manufacturing Engineers, they do all of that in 1 day. They used the saved time to make decisions on other elements of the program. That's why we like to say, simulate the build before you build. There's a lot of money to be made. 3DCS has an entire platform for dimensional engineering. Our flagship product is Variation Analyst, full-blown Monte Carlo, all kinds of distribution options, all kinds of move types. Variation Analyst is the platform to support our add-ons, advanced capabilities that allow us to use FEA data, stiffness matrices, transformation matrices, to go really deep on builds of complex assemblies. We also go the other way. We also go with an entry-level tool called Design Variation Modeler. Instead of doing 1D, worst case in RSS stacks in Excel, like you might currently be doing, do 3D worst case in RSS stacks from your CAD desktop. We asked 1,000 customers, what's the big deal? Where's the money? They told us time and again, when we do 3DCS during a digital phase of development, we reduce engineering change through the entire life cycle. When we use 3DCS to support metrology in their problem-solving requirements, we've found it to expedite that process by 50 to 60% time reduction. And we go to the launch now with multiple build scenarios and a mitigation plan. We go to the build in a proactive position, not a reactive one. We've got to tell 3DCS what is the part, how does it locate to other parts, what is the tolerance of the part. We can use a linear dimensional tolerance. We prefer the geometric dimensioning and tolerancing. What are we measuring? I need the gap in flush to be plus or minus a millimeter. Analysis, the ability to do multiple builds extremely quickly, and then evaluation. What are the sensitivities in this design to a measurement? What is most and least sensitive to my measurement? And because of your ability to embed this information, moves can be embedded as constraints in your CAD. Tolerances can be embedded as part manufacturing information in your CAD, and measures can be embedded as assembly level GD&T in the CAD. I've got with us today our Senior Technical Manager, Gerhard Bell. Gary is Senior Certified by ASME for GD&T. He's an expert in dimensional engineering and has done many digital builds in the 3DCS space. Gary will take you through the demonstration.
Thank you, Mike. So we will get started. When we refer to 3D tolerance analysis inside our integrated package, we refer to it as a 5-step modeling process. We start with the design assembly, the geometry. Because we're integrated into the CAD system, that step is done automatically. We have to define how the detail level parts index to each other. In our workbench, we call those moves. We can write those moves in our workbench, or if you are using joints and constraints, we can directly pull those in from the CAD system. And then we have to tolerance the detail level parts representing how these components are going to be manufactured, the GD&T on the drawing, your best guess. So that's going to define how we vary the detail level parts before we attach them to each other. That can be done in our workbench, or if you're utilizing embedded PMI, we can directly pull that in as well. And then finally, we have to define what it is we want to measure from a dimensional standpoint. Gaps, flushes, interference, circular clearances. So those measurements, anywhere you write a measurement, we will collect data and tell you whether or not you're going to be within your specification and all the tolerances that affected that measurement. So there's basically 3 main inputs: moves, tolerances, and measures. And once those are input, then you run the analysis and evaluate the results. If the results are out of spec, you have the option to modify tolerances, modify your location method, modify the design altogether. This is all done within the CAD system before we start actually cutting any physical parts. So the goal is to analyze your design and improve it, or at least catch as many problems as you can before you start making physical parts. So with that, I'm going to jump over to NX. And from here, you can see I have a little pulley assembly. I'm running NX, and when our software is installed, we are just another ribbon. So you can see there's 3DCS NX, and you can go to assemblies or PMI or any of the other NX functions. And when you do your tolerance analysis, you just come to our workbench. When you come to our workbench, there's going to be a DCS tree, which is associated with the NX tree. So you can see as I click through, it highlights the parts in the NX tree as well as in the CATIA or in the 3DCS tree. And then this is where all of our data will reside: moves, tolerances, and measures. This model, you can see, has embedded constraints. So we're going to utilize those to directly assemble this model. And if I take this base and open it into a new window, you can also see that these parts have embedded PMI. So remember, you don't have to have all this stuff embedded, but the idea is that as we move closer or more and more into model-based definition, we want as much data tied into the CAD as possible. And then what you're seeing here is assembly GD&T. So we're going to use those for our measurements. So because we have all this embedded, I can come up here and I can say, hey, I want to extract my moves. Well, hold on a second. I gotta get my tree back. You can see how this is all empty at the moment. And if I say extract moves, parts have to be fully loaded. It created 7 moves from the 18 constraints I showed you earlier. So if I come in here, now you can see I have these moves, and you can see how it's highlighting the features that were automatically picked up from the constraints. And now I can build this. I can separate it, and I can actually animate it through the assembly sequence, so you can see how this is put together. Now that it's built, I have not brought in any tolerances, but from the design, if I zoom in here and I hit deviate, you can see these parts are jiggling around. This is variation picked up just from the original design because the pins are smaller than the holes. So there's inherent variation in a product just from design clearances. Now if I separate this model and we look at like the base, you can see it's got some features. These were the features that are used in the moves, but there's no tolerances. So now I'm going to come up here and I'm going to extract GD&T on all the parts. And you can see it pulled in 71 GD&T callouts. So now you can see from the tree, now we have all kinds of GD&T. I'm going to double click this. I'll do a little quick auto sort so I can mouse over and you can see on this base it's highlighting that's datum A, that hole is datum B, datum C, and if I come down here, profile tolerance on that surface, profile tolerance on this surface, and so forth. So all the parts are now toleranced. If I turn the mesh on, we don't deviate the physical part, so any feature that is used for a move tolerance or a measure, we will create a mesh on it. So now if I come in here and I say sweep, you can see these surfaces are varying within their tolerance zone. So now my parts are toleranced and I have my moves defined. So if I build it now and hit deviate, you can see it's moving much more because now it's picking up the clearances plus the part tolerances. So now if you look, we have tolerances on our parts, we have move definition. Last thing we need is our measurements. So I'm going to come up here and I'm going to say extract measures. And I'll pick this here. And it says that it created 9 measurements. We're going to look at only 2 measurements. But I'm also going to come up here and extract GD&T measures. That would be like this position tolerance here. So that created 3 measurements. So now if I come down here at the final assembly, you can see that's my dimension distance measure, which is this 146 plus or minus 0.5, which is from the attachment of the bottom of the base to the center of the pulley. If I do a nominal build, you can see that updates to 54 plus or minus 0.5. If I go into this measurement, there's the 54, and this is the spec limit that it pulled from here. So this is not a tolerance. This is actually a final build requirement that we're testing for. If I deviate from here, I can click on this current, and you can see that number is changing for every build. So then our goal is to understand, with our piece part tolerances and our assembly method, can we meet that 54 plus or minus 0.5? So then we're going to continue on and run an analysis. Give me 1 second. Okay. So now you can see this is going to list all the measurements in the model. It's giving you a summary page. And if we come down to we want we want to look at this measurement here, dimension A to pulley center, dimension A to pulley center. You can see it highlights it on the graphics, dimension A to pulley center, and it's telling you your measurement, where your measurement's located, your nominal, your mean, and your spec limit, and your estimated range of variation. If I double click this, you can get your histogram here and your list of contributors down here. So this is telling us that, hey, we're not going to meet our goal of 54 plus or minus 0.5. Here's the spec limit at 53.5 and 54.5. And we're going to fail 16.53% of the time. Then, if I separate this model, I can click on here and it will walk you through all the tolerances that affected that gap or that distance measurement. So from here, you know what is your most critical tolerance, and you know what is your least critical tolerance, and you know if any of your tolerances are amplifying. You can see this tolerance here, it's a very tiny tolerance, but it's being amplified based on how these components are locating. And so with this data, you can now start validating your design, modifying your design, tuning up your tolerances. Once you have all this data, you can go ahead and build it. And then you can come over here and you can say generate a report. From here, you can choose what you want in your report, and you can choose if you want it to be HTML, Excel, PowerPoint, or Word. So I have pre-run that report, which you get right here. And so you can see, this is a cover page, took a picture of your model, pulley assembly created by me. You got a model summary. This is our default summary that you can fill in to define your objectives and your summary and your critical measurements. And when you get to your analysis results, again, you get your data in a spreadsheet format. And if I click on mouse over, you can see it took a picture of your measurement. And if I click on it, you get a better view. So we're measuring from here to the center of the pulley, and you get your histogram with your data across the top. And we even took a picture. If I hit animate, you can see we took a picture of that pulley at its min and max position. And then if I come over here to model input, I can walk through the assembly sequence, and you can see it took those moves and it took a picture to walk you through how this is actually built. If I go into my GD&T, you can see we got pictures of datum A, datum B, datum C. If I scroll down to, there's a lot of GD&T on the base. If I come down here to a profile on that surface, so now you can see, all the information in the model can be dumped out into a report, Excel, PowerPoint, Word, or HTML, or you can just dump out the results if that's what you want. And obviously you can see I'm no longer inside the CAD system. I'm reviewing this model in my Google Explorer. So that's the basics. Open up your model, define moves, tolerances, and measures, run your analysis, create a report. Thank you very much for your time.